class. And Jace is here. Excellent. So, second to last day of class. What questions do you have? Yes?
Can you ask a homework question?
Sure.
So we're having a difficulty on number 2, where we're supposed to derive an expression for the phase shift in the Fabry-Perot epsilon in terms of the thickness D, mirror surface R, and the angle between the medium stated 2.
Okay. So, what have you got so far?
Well, we have the structure. We have the two mirrors.
Okay.
The two R's. And I guess one of the things that we're kind of getting stuck with is we have the phase shift equation for, or the phase difference between the adjacent arrays, which is 4 pi over lambda naught times n to e cosine theta. And we're not quite sure where to go from there now.
Okay, so you have a situation where you've got light instant at theta 1, so inside here it's theta 2, and you can write down that the reflection coefficient of this whole thing is what? R121? Okay.
Yeah. So what was that? R12 times 1 minus e to the negative j delta divided by 1 minus R12 squared e to the negative j delta.
Okay. And this is in general complex, so we can always write as R121 e to the j, say, phi. Right? And so you're looking for the phase shift upon reflection. So what is the phase shift upon reflection?
It's a mess.
Well, I mean, it's phi, right?
Yeah.
So that's what you're looking for.
And that, I guess, when you ask for the R in the question, it's going to be that R121.
Well, yeah, so this is square root of R, this is R, so
Okay.
so now it's just algebra.
Gotcha. That makes more sense. The hardest part.
The algebra? We're setting it up.
The algebra.
Oh, the algebra is
It's just time consuming.
yeah, it's tedious, time consuming, sure, but it's not.
That's true.
Yeah, I mean, it's not mentally
I was
taxing.
like, one of my roommates was mentioning to me, he's like, oh, I love the upper classes because, like, in all the other classes, you do all this crazy math and it's just annoying. So once you get to like a high enough level, it's like you do the setup, and the rest is just algebra.
Yeah. And there's a certain satisfaction in getting the algebra done.
Yeah, it's like a solving a little puzzle or something.
Yeah. Okay, so does that do it for the question?
Yeah. Thank you.
Okay. All right, any other homework questions?
It's on the same question that we asked you already on 4B. So it's,
Okay, I don't remember that one.
Yeah,
It's already gone.
yeah, so it's showing the chromatic resolving power R for Fabry-Perot cavity is given by that equation, the finesse
Okay.
times.
So the chromatic resolving power is what?
The finesse times. Oh, I guess lambda naught.
I
over
mean,
delta
just the
naught.
definition.
Yeah, so lambda naught over delta lambda naught.
Okay. And what's the expression for the finesse?
It's the separation, phase separation, so delta, or like the actual expression, 2 pi over 4, or square root of f times 2 pi over 4, I guess.
Or also delta separation over delta 4.
Sorry, too many of them.
2 pi divided by 4 divided by the
Square root of
of
f,
f.
yeah.
2 pi divided by 4?
S square root of
Divided by the square root of f.
Yeah, there is one division.
So division between 4 and square root of f. Yeah. There we go.
Okay.
Yeah.
Okay.
Yeah.
Don't we have another expression for the finesse?
Pi square root of r over 1 minus r.
Pi square root of r over 1 minus r. Okay. Do we have another expression for the finesse?
Yeah, it's delta of the separation over delta full width half mask.
So the free spectral range over
Okay.
delta,
Yeah, the inverse of it, yeah.
delta lambda full with half max, or whatever. Okay. And what is delta free spectral range? Yeah. Let's look.
Is lambda naught squared over 2m2d.
Lambda naught squared over 2n2d. Okay. So we could write this as lambda naught squared over 2n2d delta lambda. And this delta lambda is that delta lambda, right? Okay, so we can peel out a lambda over delta lambda and call that chromatic resolving power. And then we have lambda naught over 2n2d.
Yeah, okay.
And then we could solve for chromatic resolving power.
Yep.
Yep.
That's definitely easier than,
Yeah. That's probably the easiest way to do it.
yeah.
I like that way.
Yeah. Okay. Other questions? Yeah.
So for the final, how do we submit it?
Yeah, okay, well,
Scan and email.
email to me?
Can we scan it?
We can scan
No, just do it on paper. Okay, so Thursday I'll bring the exams with me. I'll pass them out. You do the exam on whatever paper you want. Staple it to the exam that I give you, meaning the question sheets. And then when you're all done, give it to the office. Yeah.
When should we, I guess when's the last day we can turn it in?
Yeah, so what should we do?
Yeah, 'cause your daughter's coming home, right?
Yeah, on Wednesday. So,
So
Wednesday
you take-
next week.
So if you take longer than 2 days to grade it, we get 100.
No. Shoot, I forgot to bring your homeworks.
So we get 100.
Well, I already entered 100 for everyone. Yeah, because I should have given back on Thursday. But I had the homeworks and the solutions I was going to give back. Yeah, already.
So
Okay.
the same policy doesn't go for.
Doesn't apply to the final exam.
Chuckles.
Yeah, too bad. So we could make it due on Monday, or we could make it due on Tuesday by 5 p.m. And then if I do that, then I can pick it up when the office closes and I can grade it that night. That works. That'd be okay. So Tuesday, 5 p.m. next week?
Sure.
In the office? And if they give you a blank look, just tell them, hey, this is for Dr. Nordin's class. He needs to get this.
Take pictures.
Yeah, take pictures. Always a good plan. Oh, and Thursday, let's see, in our department, we've got President Worthen coming to have lunch with us between 12 and 1. So let's start class at 1 on Thursday. And of course, we'll end at the normal time, or earlier. Okay?
Will you bring both solutions on Thursday?
Yes. I remember. But I should remember. Okay, other questions?
Yes, I have a question.
Okay.
From the reading, I've thought about it some, but it's still not entirely clear to me. So we do dielectric stacks to make a mirror, and then there's also dielectric stacks to make like the opposite, an anti-reflection coating.
Mm-hmm.
And as far as I can tell, it's for the stacks to, so the difference between those two, I guess, is what I'm trying to kind of understand. tell me if I'm thinking about this right, whereas for the anti-reflection coating, you kind of gradually decrease the index of refraction between one and the other. But for the mirror, you are having these sharp reversals of reflection coefficients.
Yeah, so for an anti-reflection coating, singular anti-reflection coating, you need a film with a refractive index intermediate between the substrate and the ambient.
Yeah. Yeah. But like in all our examples for the mirrors, though, they were all intermediate also between both.
No, not necessarily. I mean,
for the homework problems, we did like 6 and 7, they all had them.
yeah, and that's just kind of how they worked out.
Yeah.
Yeah.
Oh, okay.
I mean, it doesn't really matter what the substrate index is when you're building a mirror.
Okay.
And it doesn't really matter what the two film indices are, just so long as they're different.
Yeah.
That's all that matters. Okay. You've got that, you can build a mirror.
Okay, so mirror, so I guess an anti-reflection is a very special case of, okay.
Yeah. Yeah, you're going for something very specific there. Yeah, and then in the very last part of, I think, problem 7, it asks, what do you get from what you just did?
Yeah.
And what do you get from that? How many have done that problem? 2? Okay. Okay, well, we can chat about it on Thursday.
So I can share what I can tell you what I got. If
That's okay.
not.
Oh, go ahead. It should be pretty obvious once you've done those 2 problems.
Yeah.
Okay, anything else? All right, so last time we finished off 2-layer anti-reflection coatings. We looked at how they perform when you're operating at the wavelength, or at a wavelength different from what you designed it to be for. And we looked at what happens as you go off normal instance, if you design it for normal instance. What's your takeaway from those things?
For me, it's like if you know what angle you're coming at, you can find an optimal design. Generally, if you're going at an angle, they're less effective.
Yeah, so basically, single-layer error coatings are very nice, but
Multi-layers.
you almost never have the right refractive index. So if you need really low reflectance from your anti-reflection coating, you're probably not going to get it with a single-layer coating, which means you got to go at least 2 layers. You do 2 layers, then yeah, you can do fantastic at your design wavelength and at your design angle. But when you go off your design wavelength, it's going to break down. When you go off your design angle, it's going to break down. But
and that always happens, right?
yeah, always. It's always how it goes. Because it's an interference phenomenon, and when you screw up the phase difference that you're going for from layer to layer, then you mess up the interference phenomenon. And then you mess up the constructive or constructive interference that you've been trying to achieve. That's always how it works. Okay, so then we started talking about absorption and dispersion, and we saw that if we have some material and look, and we've got light instant on it, if we look just inside that material, call the irradiance there I at 0, call that the z-axis, then the irradiance here as a function of z is I at 0 times e to the minus alpha z, where alpha is the absorption coefficient. And then we wanted to tie that back to the permittivity. And so we noted that for an absorptive material, then we can let the electric susceptibility have an imaginary part in addition to the real part. And if that's true, then our permittivity has an imaginary part as well, and our dielectric constant has an imaginary part. And then what we found was that we can write the refractive index as having an imaginary part as well. And so we went through, kind of the math of that and how it all worked. And then what we found, and then of course, if you know the real and imaginary parts of the refractive index, then you can always get back and calculate the real and imaginary parts of the dielectric constant or the electric susceptibility, or vice versa. If you have one of these things, you can always go to this. It's just algebra again. And what we wanted to do is connect this to that, and what we found is that the absorption coefficient is equal to 4 pi over lambda naught times the imaginary part of the refractive index. And so there's a direct relationship between the imaginary part of the refractive index and the absorption. If the imaginary part of the refractive index goes to 0, the absorption goes to 0. And this thing, what do we call it?
Absorption coefficient.
Absorption coefficient. And this thing, what do we call it?
There's a letter that we were mad about.
Okay.
Yeah, that's right. Yeah, some in some areas of optics you call it K, which is annoying. It's the imaginary part of the refractive index. It's also called the extinction coefficient. Yeah.
So what does that mean about does it mean that it's more susceptible to making like dipoles and that's why it loses more energy, or what exactly does that, the higher that mean, what does that mean about the material?
Well, so
Because the energy is going into the,
it's going into the material. So it's basically, it's kind of like a coupling coefficient from the energy in the propagating wave to energy dissipated into the material itself.
okay.
Yeah.
Does it include all forms of loss? I mean, heat losses as well as, say, transmission losses?
Not transmission losses.
Okay.
Well,
I mean,
transmission losses.
Because the effect,
Sorry, I was thinking you meant at an interface, but you mean just
I mean,
as you
like
propagate.
it radiates off into space, and so you lose energy to the material.
I would amend that to say any mechanism whereby energy is coupled from the propagating wave to the material, regardless of what the material does with that energy.
Okay.
Yeah, it takes into account all of that.
Okay.
Okay. So, let's get a feel for kind of how this works. Let's say that our material is silicon, and in fact, let's say that this silicon, it's actually a photodetector. And so we have light coming in. Some fraction of it makes it through the surface. We'll talk about how much makes it through in just a minute. But we have some irradiance just inside the surface. And then as it propagates, presumably, if it's a photodetector, we're going to absorb it. And really the starting point for everything is, what are the optical constants of silicon? So whenever we say optical constants, what we mean is the real part and the imaginary part of the refractive index. Once you have those two things, you've got everything. You can calculate whatever you need. And so for silicon, let's say that we're talking about a wavelength of 500 nanometers, and you always have to specify the wavelength for which you are looking for the optical constants. We'll talk about that in just a few minutes as to why. But at 500 nanometers, the optical constants for silicon are, the real part is 4.281. The imaginary part is 0.055. And you look at that and you say, wow, 0.055 compared to 4.281? That's really And yeah, it is small, but it is not negligible. Because if we calculate the absorption coefficient here, we've got 4 pi over 500 nanometers. And then we've got the imaginary part of the refractive index, 0.055, and then usually we want inverse centimeters, and right now we've got inverse nanometers. So let's do 1 centimeter is what? 10 to the 7 nanometers. Okay, so we work that out and we find, oh, that's 13,800 inverse centimeters, which is gigantic. If we did an inverse microns, this would be 1.38 inverse microns.
Wait. Yeah, shouldn't it get like a lot bigger if you got a micron?
No.
Oh wait, because it's inverse.
Yeah.
Okay.
Yeah. So basically, if you look at the irradiance here, and look at the ratio, it goes as e to the minus alpha z. And if alpha is 1.38 inverse microns, how big is z before that becomes 1 over e? Mm-hmm. Yeah, so the 1 over e point, 1 over e distance is 1 over 1.38 inverse microns, which is about 0.7 something microns. So, 725. So within 3/4 of a micron, you've already lost the majority of the power. Okay. So are you familiar with how silicon photodetectors work? Okay, so you have,
Get electric current out of them.
yeah, you get an electric current out. There's a p-doped part and an n-doped part. So let's say that this is p and this is n. And so this has an excess of holes, right? This has an excess of electrons. And so in the junction, the electrons and holes annihilate, and we leave behind the nuclei. And so what direction is our built-in electric field at the p-n junction?
Without anything hitting it, right?
Yeah, with nothing hitting it. Yeah, we're just setting it up.
Electric field is opposite of voltage.
So we basically have an excess of holes over here, right?
Yeah.
Excess of electrons over there.
Well, seem to remember it's reverse.
Yeah, it's a reverse field. So we have to have an electric field in this direction to keep them apart. And that electric field is generated by the exposed nuclei here from the holes and electrons annihilating at the junction. Okay, so the point is we have a built-in electric field at the p-n junction. So if I have some light, instant, if I have a, let's say a single photon comes in here, and it gets absorbed, then I generate a hole and an electron. And if I'm in this region of electric field, what happens to them?
They'll get separated.
They'll get separated,
That's only in the depletion.
only in the depletion region. So I get a photo-generated current for any light that is absorbed in the depletion region. So if my depletion region is, say, 5 microns underneath the surface,
You're not gonna get anything.
you're not going to get a thing. Because all the absorption happens much closer to the surface. On the other hand, if my depletion region is, say, here, within, say, 0.3 microns of the surface, it's not going to be very efficient because a lot of the absorption happens beyond 0.3 microns. Yeah.
This 0.275 is like a Gaussian of like this is the most probable place where the
No, it's just the 1 over e. So this decays exponentially.
okay. But as photons, if you're sending a bunch of photons there, they're not all gonna.
Yeah, I mean that 1 over e exponential decay.
Exponentially decays from the initial surface as you go deeper.
Yeah. And so for an
Sure.
individual photon, you can look at that as a probability density function. For a whole ensemble of photons, it's just, that tells you the distribution of power loss as you go through. Yeah.
So that 0.725 has to do with, I guess, the point at which the radiance has gone.
Down to 1 over e of the initial irradiance.
Okay.
You know, or we could say, hey, at what z is this equal to, say, 1/10 of the initial irradiance? And so that would be e to the minus alpha z, and let's just call it 1/10. So we could solve for z 1/10 of the irradiance, and we end up with 1.67 microns.
So I guess what I'm confused about is if the depletion region is below 0.725, then why is it inefficient?
Well, it's just that here, if I plot irradiance as a function of z,
It goes down.
it goes down like this. If my depletion region's out here, I've got almost no photons.
All right, but if it's at 0.3, that's way below 0.725.
Well, then I'm just going to pick up these photons. All those don't do a thing for me.
Yes, you want a really wide depletion region really close to the surface.
Yes, that's right. So what you really want is a PIN photodiode. Yeah, so you have this P region here, and then you have an intrinsic region, and then you have an N region here. And now your field extends over a much wider region. And so now you have that wider region being sensitive to absorption events. So in that case, you know, if now this is your PIN junction region, your depletion region, now you get all of those photons contributing to photogenerated current. It's much more efficient. Okay. And notice all of that just falls out of knowing the optical constants and that simple fact, combined with Beer's law. And it's pretty straightforward. And now you pretty much know how you want to design a photodiode. Okay, any questions? All right, then let's.
There is also like speed considerations because the wider that depletion region is, then you get slower.
Yes, exactly. And like everything in science and engineering, there's always trade-offs. And so knowing what it is you need to achieve and what is going on with the phenomena, then you can play the trade-offs to get what you need to achieve. But you're always going to give up something in order to get something. That's how it generally works. Yeah.
So when they talk about like super absorptive materials like the Manta black or whatever, are they saying that alpha is super high such that they claim like it absorbs 99.999% light, right? Is that like within a certain distance that they're expecting that?
Yeah, so it depends on the physical mechanism they're using for the absorption. And also it will always have a wavelength dependence, which we'll be talking about. So kind of depends.
So when they throw out like that 99.999, that doesn't necessarily directly relate to alpha.
It does, but it's also, there's an assumption as to what the spectrum is that's instant on the material.
Right, so it has to be the right spectrum, otherwise that statement is wrong.
Exactly. Yeah. And then you also have to take into account what's happening at the interface, which is what we want to do next. So we basically said, hey, we're going to look at the irradiance just into the material. So we haven't accounted for the fact that in general, we have Fresnel reflection at the surface. So we're going to lose some light at the surface. So we know how to calculate Fresnel reflection for the case of dielectric materials that have no loss, they're not absorptive. So the question is, what happens in the case where we now have a non-zero imaginary part of the refractive index? How do we calculate the Fresnel equations or the equivalent of Fresnel equations for that case? And it turns out that it works out awesome without doing any more algebra. And I'll just assert this, but you could always go back and prove to yourself that it's true. It turns out that the reflection coefficient that we calculated for the fields is the same, whether we have absorptive or non-absorptive materials. So in other words, we calculated, let's see, for the S state, that the Fresnel reflection coefficient was N1 cosine theta 1 minus N2 cosine theta 2 over the sum of the two terms. And we derived that for the case where material 1 was a dielectric material and material 2 was dielectric, and they were non-absorptive. But it turns out that if we have an absorptive material, meaning the imaginary part of the refractive index is non-zero, it's the same expression. So we could plug in, let's say that material 2 was absorptive, material 1 wasn't, then we would have N2 prime cosine theta 2 plus J N2 double prime cosine theta 2. In other words, we just substitute in the imaginary, or rather the complex refractive index for N2. And then this would be N1 cosine theta 2 plus N2 prime cosine theta 2 minus J N2 double prime cosine theta 2. Make sense?
Sorry, why is theta 1 equal to theta 2?
Oh, because I messed up.
Oh, okay, all right.
Thank you very much. Yeah. Yep. So in other words, the Fresnel equations are still valid. Just plug in the complex refractive index for whichever material is absorptive. And you're good. And so calculating the reflectance then means we have to take the magnitude squared of the reflection coefficient because it's complex. And so if we do that, we have N1 cosine theta 1 minus N2 prime cosine theta 2 quantity squared plus N2, N2 double prime, no, N2 prime.
One prime.
N2.
The above also, sorry.
Pardon?
In the above equation also, isn't it? And
Oh, yes, thank you very much. Perfect. So N2 double prime cosine theta 2 quantity squared. And then in the numerator, we have N1 cosine theta 1 plus N2 prime cosine theta 2 quantity squared plus N2 double prime cosine theta 2 quantity squared. And we could do the same thing for the TE, or rather the TM reflection coefficient. And then if we look at normal instance, then the reflectance becomes N1 minus N2 prime quantity squared plus N2 double prime squared over over n1 plus n2 prime, quantity squared plus n2 double prime squared. And so this is for the S case. And when we do the P case, of course, it'll be the same at normal instance.
So, should they be double prime on the first instance of the primes? Should it be double prime or single prime for the real part?
Oh, yeah, you're right, thank you. Yes, you're right. Yeah, perfect.
Wait, where was that?
Right here,
Oh, wait, single prime and
or
double
right
prime.
here, yeah. Yeah,
Oh, yes.
yeah.
That makes sense.
Okay. So now, so number one, the reflectance at normal instance or non-normal instance, it's easy. If we have the complex refractive index, it's no big deal. So let's go back to our silicon case. So we end up with Rs is equal to 1 minus 4.281 quantity squared plus 0.055 quantity squared over 1 plus 4.281 quantity squared plus 0.055 quantity squared. And now, is this 0.055 making any difference?
Not really.
Nah, not really. It's pretty much negligible compared to what's going on here. And so we calculate this, it's 38.6%. So on our silicon photodetector, we're losing 38.6% of the incident light as reflection, which is pretty typical. Unless we do what to the surface?
AR coatings.
AR coated. And if we put an anti-reflection coating on it, now we have a wavelength dependence of the reflectance. So if we want a broadband detector, probably ought not to do that. And just take the loss and account for it when we calibrate our system. Okay.
That only would apply to 2-layer AR coating, right?
Oh, single layer too.
I thought the single layer was pretty flat.
Pretty flat. I mean, it depends on what you're trying to do with it and how accurate you're trying to be. Yeah.
Putting an AR coating gives you, really good for one wavelength.
If you have the right refractive index for a single layer AR coating.
What does it do? What would it do to the RS of the other wavelengths?
Well, I mean, it will affect them. So,
Would it increase it, decrease, or it just depends?
well, remember, if we look as a function of wavelength, what the reflectance is for a single layer AR coating, it does something like this. And here's our design wavelength. So it doesn't fall off very quickly. It's just that this isn't down here because we don't have the right refractive index. But if we do a 2-layer, then it's going to look, more like this. We can get much smaller reflectance, but the bandwidth isn't as wide.
Is the absorption loss in an anti-reflection coating somewhat negligible because it's so thin?
Well, there's only absorption loss in the anti-reflection coating if it's absorptive.
Right. So not all materials.
Yeah, generally you choose material that's not absorptive for the AR coating. Although I'll show you an example that is completely the opposite. Okay. So, what do you learn from this?
There's a lot.
There's a lot. Well, just this is awesome because if you've got these guys, then you've got the absorption coefficient. You can easily figure out what's going
So
on.
those vary by wavelength.
wave by wavelength, which is what we're gonna dig into, understand how that works. And then calculating the reflectance is no big deal. Just the Fresnel equations with complex refractive index.
So is this absorption coefficient what makes certain materials have certain colors? Because the absorption will change across the spectrum?
Yes, as long as it's not a thin film phenomenon, yeah. That's it. Yeah, and we'll look at some of that. Okay, so now before we dive into wavelength dependence of these things, let's just go back to this for a moment. So for normal instance reflectance, just looking at that equation, we can determine how you make a really good mirror. So good mirror means what? High reflectance. So looking at that equation, how do you get high reflectance?
Really big difference.
Yeah, really big difference in the real parts will give you high reflectance. But what's the biggest real part of the refractive index that you can have?
4 point something.
This is gigantic.
Yeah, doesn't get much bigger than that.
Doesn't get much bigger than that. So this is on the order of 4. And so if N2 double prime was 0, and this is on the order of 4, then RS is about 36%. So if you try to get a good mirror by having very high real part of the refractive index, you'll get to maybe, a third of the power reflected. And here for silicon, that's about ballpark-ish where we're at. So that's as good as you can do.
That's for just a single, like, one material into another.
Yep. Mm-hmm.
Like a Bragg mirror.
Yeah, then it's a different ballgame. But here, for just a single interface, that's one way you can play the game, and clearly that's not a very effective way to play the game. So, just looking at the math, what's the other way you can play the game?
The imaginary part.
Yeah, if the imaginary part was huge, let's say the imaginary part was 100. This is about 4 maybe, then this doesn't matter. And you get 100 squared over 100 squared, which is pretty close to 1. That gives you a really high reflectance. So the question is, are there materials where the imaginary part of the refractive index is gigantic and the real part is, relatively small? And the answer is yes. There are such materials, and you know them well. They are called metals. So if we look at some metals, and then let's consider a wavelength, and then let's look at the real and imaginary parts of the refractive index at those wavelengths, and then calculate the reflectance. Let's see how it works out. So let's consider aluminum. We know aluminum makes a nice mirror. We stare into a bathroom mirror that's made out of aluminum every day. And so let's go in the green, 517 nanometers. Then the real part of the refractive index is 0.826. That's not very big. The imaginary part is 6.283. That's big. It's not absolutely gigantic, but it's big. The reflectance is 0.923. It's over 90% for the reflectance.
Pretty good.
Yeah, it's not bad at all. And it's cheap, so that's why we have such mirrors in our bathrooms. On the other hand, if we look at gold, also at 517 nanometers, the real part of the refractive index is 0.5. The imaginary part is 1.86. So the reflectance is 0.647. It's high, but it's not really close to 1. If we go to 1.55 microns, which is the telecom long haul fiber wavelength that you use, the real part of the refractive index is 0.18, it's tiny, and the imaginary part is 10.21, so that the reflectance is 0.993. It's awesome.
That's right.
Gold is awesome in the near IR. It's a fantastic reflector. If we look at 3.1 microns, then the real part is 0.59. The imaginary part is 20.83. So the reflectance is 0.995. It's even better. And if we go out to 6.2 microns, the real part of the refractive index actually starts to get kind of big, 2.13, but the imaginary part, 41.73. So the reflectance is still about 0.995. So gold is fantastic in the infrared as a mirror. It just works great. If you take a look at silver, go back to the visible, 500 nanometers, then the real part is 0.24, so it's very low. The imaginary part is 3.09, and even though that's not that big, still, the reflectance is 0.914, so over 90% for silver. So, bottom line is, you can make a really good mirror if you have a material where you have a very large imaginary part of the refractive index. And so, metals fill the bill there. Okay, any questions?
So the margin two, it's super absorptive to, depending on the wavelength. This is like why metals get hot when they leave on the sun, right? Because they're absorbing all that light.
Sort of. I mean, what this is saying is that when you get the absorption really high, what happens is most of the power reflects.
Right, okay.
And in a metal, you know, what's the physical mechanism? Well, the instant electric field sets up a surface current. The surface current radiates power, and then radiates it in the opposite direction. And another way to look at it is this very high absorption means that the field doesn't penetrate very far. If you calculate skin depths for metals, you know, they're really, really small. Yeah.
Where's a good reference for data like this? I keep looking for it, and it's not in the book. There was like this handbook of chemistry thing you mentioned at the start. Like that's kind of
CRC
hard
handbook?
to use. Yeah, that was.
I got these out of the CRC handbook.
You did.
Yeah.
Okay, because the online version I found is extremely difficult to search through.
Yeah, and I have not really looked at the online version because when I was active needing this stuff was before the online information was very good. This is in the 90s. So for me, as a practitioner, it was always crucial to have that big fat CRC handbook on my shelf.
So it's probably changed now, 2009. It's probably changed now, 2009.
Yeah. Just because it's old doesn't mean it isn't good. Yeah, old data can be really good data. Yeah.
Yeah, if it was really good, then nobody had to repeat it, right?
Yeah, exactly. That's right.
All the global warming is changing.
Yeah. Yeah, global warming. Don't get me started. Which isn't to say we aren't dumping carbon dioxide in the atmosphere. Of course we are. It's just what's the effect. Okay. Now, you might notice over there on that chart of optical constants for metals that the real part of the refractive index is kind of weird. How could it possibly be less than 1?
Yeah, that is weird.
Yeah. So that's the thing we want to attack next. And this gets back to our next topic, and that is dispersion. So we just talked about absorption. Now we're going to talk about dispersion. And dispersion means, we define it as the variation or change of the real part of the refractive index with wavelength. So whenever we say dispersion, we mean something that's very simple. Just that, oh, the real part of the refractive index changes when the wavelength changes. That's all it means. So let me show you an example here. You could flip on the
My eyes going down, focus on.
Yeah.
That's interesting. Man, something's up.
Yeah. You see that okay? All right, so check this out. Here's refractive index, meaning the real part of the refractive index, as a function of wavelength. Notice this is a log scale. So visible is, 400 to 700 nanometers, just right over here. Here we're in the UV, here we're in the infrared. And here's a whole bunch of different materials. So sodium fluoride, let's just look at it. Notice here, deep in the UV, the refractive index looks like 1.4. And as we go towards, wavelength.
Yeah.
Yeah, right here's the visible. As we go into the visible, it's relatively flat, but not perfectly flat. It decreases a little bit as you go the longer wavelength. And then out over here, once you get into the infrared, eventually it dies off. It starts to really die there. Fused silica, same behavior. Calcite, same behavior. Sapphire, same behavior. Titanium dioxide, same behavior. Silicon, oh, look at that, germanium. And by the way, look at silicon. This says 3.4-ish, but I had 4.281. What was the wavelength for 4.281? 500 nanometers, which is over here.
It's outside of there.
Yeah, in fact, why does that cut off? Is there suddenly no real refractive index once you get to a wavelength shorter than whatever that is?
This is the infrared handbook, so it's
Oh, who cares? Just look at the data.
obviously it just wants the infrared stuff. So it's wanting.
Yeah, I mean, so that's the usual human pattern matching approach to try to figure something out, which is an awesome and effective approach in many cases. But in this case, it'll just distract us.
So your question is why it doesn't show that?
Yeah, I mean, the real part of the refractive index, does it not exist?
No, it exists.
It exists, of course. So the reason why they've cut it off and not shown you is they're only showing you the portion of the wavelength range in which the material is transparent, meaning not absorptive.
Okay.
So for silicon, everywhere to the left of a little over a micron, it's very absorptive. And clearly, if we're going to get up to 4.82, this is going to go screaming up there to 500 nanometers. So, okay, so we're going to want to understand that, but just be aware that's why these things cut off. If we take a look right here, expand it on a linear scale, refractive index for several different types of glasses. Borosilicate glass, I mean, that's just the everyday glass you see everywhere, windows, microscope slides, etc. And you can see at 0.4, which is where our eyes cut out on the small short wavelength end of the spectrum, is about 1.53-ish. Over here, 0.7, it's about 1.52-ish. So over the spectrum that we can see, then refractive index is decreasing. So basically, that's the dispersion of borosilicate glass. Light flint glass, dense flint glass, where we just put other elements into the glass to pop up the refractive index and make it higher. But it has the same sort of characteristic relationship as a function of wavelength. And that is called normal dispersion. So when the refractive index decreases as the wavelength increases, that is normal dispersion, which is distinct from not normal dispersion, which we'll talk about. Okay, so let's flip that guy off. Okay, so what we want to do is kind of understand how this works and where this normal dispersion comes from, and then we want to see what anomalous dispersion is and where it comes from. And it turns out that if we have a material where refractive index is a function of wavelength, then that means that the material is absorptive. Doesn't mean it's absorptive everywhere for all wavelengths, but for some wavelength it is going to be absorptive if the refractive index varies with wavelength, and all materials do. So, if the material is absorptive, then it is also a function of wavelength. That absorption is a function of wavelength. And it turns out that there is a linear shift invariant relationship between the electric polarization and the real electric field. And these two things are real. And because they're real, then this linear shift invariant relationship, I mean, basically the transfer function goes as the permittivity of free space times the electric susceptibility, which is a function of frequency, meaning it's a function of wavelength. And if these guys are real, then it must be that the electric susceptibility is symmetric. Therefore, if we look at the electric susceptibility as a function of negative frequency, it's going to be the complex conjugate of the electric susceptibility at that frequency. And because there's a causal relationship between the electric polarization and the electric field, because all physical systems are causal, then taking all of those things together, the real and imaginary parts of the electric susceptibility are related, and they're related by a very particular relationship. And that relationship is that the real part of the electric susceptibility as a function of frequency is equal to 2 over pi integral from 0 to infinity of dummy variable s, the imaginary part of the electric susceptibility as a function of s, over s squared minus nu squared ds. So we're integrating over the dummy variable s. And similarly, the imaginary part of the electric susceptibility is equal to 2 over pi integral 0 to infinity of nu times the real part of the electric susceptibility as a function of dummy variable s over nu squared minus s squared ds. And these are called the Kramer's-Kronig relations. So, if you have the real part of the electric susceptibility, you can calculate the imaginary part. And likewise, if you have the imaginary part, you can calculate the real part. Now, having this in terms of electric susceptibility isn't that useful. Remember, electric susceptibility, we could convert it to the complex dielectric constant. We could convert it to the real and imaginary part of the complex refractive index, or we could go back the other way. Or we could do this in terms of real part of the refractive index and the absorption coefficient. Whatever. I mean, they're all related, so it's all just just algebra to go between them. So let's go to this pairing right here, because it turns out, I mean, it's easy to calculate the absorption coefficient as a function of wavelength. It's really easy to measure. And because that's easy to measure, we can use the Kramer's-Kronig relations to calculate the real part of the refractive index. And so usually that's the direction we go. So let's write the real part of the refractive index as a function of photon energy. So photon energy is just h nu, which is equal to hc over lambda. So we'll write that real part of the electric, or rather the real part of the complex refractive index. Doing the algebra to do the conversions, we end up with 1 plus hc over 2 pi squared integral from 0 to infinity of the absorption coefficient, dummy variable E prime, over E prime, quantity squared, minus E squared dE prime.
What's the HC again?
H is Planck's constant.
Planck's constant.
C is speed of light in vacuum.
Is that? So when do we use that from the E equal to hc? Is that still like electromagnetic model or?
No, this is the energy of a photon.
Oh, it's energy now.
Yeah, it's not electric field. We're double dipping again on our symbols.
Yeah. I knew that. I don't know why.
So why do we leave E squared in the bottom, but we've converted the E out here into H over 2 pi squared? Oh wait, we don't have a lambda.
Yeah, we don't have a lambda.
Okay.
Yeah,
never mind.
but this HC comes because of this thing.
Yeah.
Yeah. When we're doing our conversion of the variable of integration. Yeah. So we skipped a whole bunch of algebra. But this is the useful and the interesting part, because once we have measured the absorption coefficient, we've got it all. We can get the real part of the refractive index by just calculating it, which is super useful.
And then we can also get the imaginary part too, right?
Yeah, I mean,
What other-
the imaginary part comes directly from here, because alpha is equal to 2 pi delta 4 pi. 4 pi what? Yeah.
So you just measure absorption over all those frequencies you care about, and then you have the refractive index.
So you take a spectrometer like the one in our lab, measure the absorption over whatever wavelength range you're interested in. Do this integral, now you have the real part of the refractive index over that wavelength range. Works great. Yeah, tell us.
So what is the E prime is? that
Just
percentage
the
energy?
it's the variable of integration.
Okay.
Oh.
Oh, okay.
So would that spit out the average refractive index over whatever range?
Because this is as a function of that photon energy. Me, it's a function of frequency or a function of wavelength. So you measure the absorption as a function of wavelength. Use this, you calculate refractive index as a function of wavelength. Yeah, works excellent. Next time I'll show you an example of where we had to do that years ago. It works really well. Okay. Any questions? Okay, so we're about out of time. What we'll do next time is wrap this all up. I mean, basically, this ends up telling us where refractive index comes from, in some sense. And it comes from absorption. And what we want to do is take a look at what this equation says, if we have some absorption band, what it says about refractive index everywhere as a function of wavelength. And it turns out what it says is really interesting and explains a lot about rheometers. So that's what we'll do on Thursday, is go through that. Okay, well, we will see you Thursday.